So today we're going to look at SPECT, basically, or single photon emission computed tomography. And the distinctive feature about SPECT, which is kind of cool, is that the patient themselves becomes the source of radiation. And so you inject a contrast agent, excuse me, a liquid contrast agent into a patient, and it has a radioactive substance in it that emits very low energy gamma rays or high energy X-rays, are about 140 kV. And but the patient themselves is essentially glowing, and our eyes aren't sensitive to photons up there, but if you had glasses on that would be sensitive, that patient would be shining, amongst who's ever in the room. And this slide shows the sort of the difference between an emission technique and a transmission technique. And transmission, we're all very familiar with. We've all had X-rays of our hand or our chest or whatever, where you have a source of radiation down here. And that radiation can be anywhere from 40 kiloelectron volt X-rays up to 140. And you shine this light, this X-ray light, through the patient and look at the shadow cast by the patient with your detector. And so the bright zones in this image of this patient's chest that are seen on the detector are those places in the patient in which a lot of X-ray absorption has occurred. And so therefore, you basically, in the old days when this was a silver iodide film, you would not expose the film. And so therefore you would get a very bright signal. And then where the X-rays got through and exposed the film, you get a dark signal. So it's a negative, essentially. And so this is, a map of the absorption of X-rays through the different pathways through the patient. Contrast that to SPECT, in which we, take the patient's decubital vein and we inject substance in there. And normally you wait some time for that substance to essentially circulate through the body and then accumulate in various organs, right? It's done a lot for cancer in looking for essentially if you have very small metastasis in different parts of the body and you need to scan the entire body to look for them, you can use a method like this, where if you get little point sources of radiation, these metastatic lesions take up this contrast agent preferentially and then give a very sensitive estimate of whether or not there's some kind of metastasis from a primary tumor. For our application in cardiac, we would like to look at the heart. And so the agent gets taken up by the myocardium, and then we take images of the myocardium over the next 20 minutes or so after injecting a contrast agent. Excuse me. So the patient themselves, because of this contrast agent, are emitting these 140 keV photons, and then we have some kind of detector and we can see where those photons are. Granted, this is a kind of a blurry image because the detector itself traditionally is not that great, right? It's a low resolution detector, and compared to the detector used for X-rays. So this is the geometry of a SPECT scanner, sort of a modern SPECT scanner used for cardiac imaging. And the detectors themselves that will detect those gamma rays coming out are organized to wrap around the patient as maximum as possible. And then this whole gantry can rotate freely around the patient to get different angular views. So this person's lying there, and they're going to lie there for, anywhere from 5 minutes to half an hour and these gamma rays will come out of their body and get detected by this guy. Usually you leave the detector in one angular configuration for a finite period of time, let's say 30 seconds, a minute, and you get that view, and then the whole thing clicks around and you get another view. And so you add up your views that way. And we'll get right to the heart or what is created by this scanner right off the bat here. And so this is a very busy slide, but we'll just walk through it carefully. So these little donut shapes here are slices of the heart, and this are the left ventricle. So here's the left ventricle. This is a 3D model of the left ventricle, and on problem set 1, you guys created 2 types of left ventricle, one that was a cylinder and one that was a sphere. They're usually somewhere in between. And but a short axis view of the left ventricle looks like a donut, and that's when you cut it along one of these planes that cut through the left ventricle. And so you can see the myocardium all the way around this short axis view. And when SPECT images are shown, and then the brightness here corresponds to the amount of radiation that was emitted from this point, right? So that's what the brightness means. And then the reason that you have 2 rows that look very similar is because the top row is the amount of radiation after the patient has been stressed. And so stress can be giving them a pharmaceutical that increases their contractility or their perfusion. Or you could put them on a bicycle and create higher blood flow in their myocardium to see if the myocardium or the heart itself, the system, can respond to that stress. And so that's this top row. And this row here is what that person's heart looked like at rest. So rest can be done either after the stress or it can be done before. So their heart rate is a normal heart rate, and they, have the sort of baseline myocardial blood flow. And so if we look at just the stress, so this row here is stress, this row is stress. And what we're doing is we're going from the apex of the heart, which is right down at the bottom here, right at the tip of the heart. We move our way up towards the valve plane on each one of these views. And then we go, this would be sort of around the middle of the heart. You can see sort of a right ventricle shape here, all the way up to where the valve plane is. Right? So that scans through the entire heart. The point of these images is to map where is abnormal flow, if it exists. Where in the heart does that abnormal flow exist? And so these are short axis views. These views, this one and this one, are long axis views. And so these are views where you have the apex in view. One of the, say this could be the septum and this could be the inferior lateral wall. And you have a horseshoe type of view in which you look at the heart from the side. So you're looking at it from the angle that we're looking at here. And then you rotate the heart around and look at different angles. If you look at these maps here, they're colorized sometimes just to increase the visibility of abnormalities. But all the color corresponds to is a single scalar value that either goes up and down. But here the bright white to orange means there's high perfusion, and this purple means there's low perfusion here. And so the asymmetry of the perfusion map here is an indication that there is low blood flow in this part of the heart. And this is done millions of times a year. Cardiac SPECT scans are done for people who have suspected abnormalities in their blood flow to their heart. You can see on this one, it looks like there might be some kind of low blood flow right at the apex of this heart here in the long axis view, etc. And so the quality of these pictures is mostly wrapped up in the ability to actually estimate the blood flow as opposed to a high resolution picture of the morphology of the heart. This is, as you can see, it's a very low resolution map of the blood flow. If you want to look at all of the heart at one time, you can reconstruct a three-dimensional model and then rotate it around to look at the various brightness in different locations in the myocardium. Here, it looks like on this posterior wall, we have a chunk of tissue that is not being perfused normally. If you want to flatten this 3D model out so you can see it all in a two-dimensional plane without having to manipulate the 3D model with a mouse or something, you can make a graph that looks like this, and this is called a bullseye plot. At the bullseye, right in the middle, is the apex of the myocardium, so that's this point right down here. And then the rest of the heart is mapped out radially such that this circle here corresponds to one of these very basal short axis views here. And then as we move towards the middle, down towards the apex, we move down the heart this way, right? So base, move down to apex, and then this is the anterior wall. The patient's chest would be here above it. This is the lateral wall, so the left arm would be over here. This is the septum, so the right arm would be over here. And then this is the posterior wall, and so the patient's back would be down here. So the classic view or orientation is you're looking towards the apex of the patient's heart, and you're looking from their feet towards their head. And then it's mapped out into a two-dimensional map like this. So the great thing about these is, you know, you can print this out on a little piece of paper and you've pretty well got the whole map, right, of where the blood flow is normal, so in these orange areas, and where it's abnormal in these blue areas here. Any questions about that? That's the, now you could go read these scans. They're not that hard to read. And the other amazing thing about them, as you can see, because of their spatial resolution not being great, there's a lot of leeway in the interpretation of these scans. So that's good news and bad news. The bad news about it is, because there's a lot of leeway, you're going to get high variability in reads depending on who's reading it. The good news about that is, if you are the cardiologist, it gives you a lot of freedom to keep pushing the patient through a diagnostic protocol or stopping and saying, oh, you're fine. Which that sounds kind of ironic. You say, well, why, you know, do you really want to give a physician that much freedom because the data is noisy? And sometimes you do. Sometimes, you know, having a good cardiologist who knows all of the other clinical data and everything, it's good to give them a lot of freedom. Because if they're experienced, they're, you know, humans are a really good sort of deep learning network. So this imaging technology is fascinating from an economic standpoint and from a medical practice implementation standpoint, in that its growth over, you know, 10 years or a decade was absolutely astronomical. A few papers, you know, were written in the mid-90s showing that this was a good way to predict who needed further intervention in heart disease versus those people who didn't have, you know, a flow limiting lesion in their heart. And you can see over the course of from 98, when there was, you know, about $250 million spent on this test in Medicare. This is just Medicare Part B payments. This is not the whole healthcare system, right? But it's indicative of what's going on. It's just there's better records here. And then over the course, you know, about 8 years, it gets up to close to $1 billion. You know, so it's this incredible growth right here. And it's not that the procedure itself got more expensive, you know, that's increasing the revenue. Is the fact that so many more people are getting it. And this is the rate per 1,000 patients in the Medicare Part B, excuse me, who get this test when they show up at the cardiologist's office. And so here you have 15 out of 1,000 in 98, and now we're already, up to 50. So it's hard to compare this with any other technology other than, say, MRI in the early days of brain MRI in the 80s, when it was discovered that you could unequivocally diagnose a few things like MS and things like that with MRI. Then the uptake of the technology was extraordinarily fast. Here, what's going on is that this imaging machine, over this time was available in the cardiologist's office. So it was extraordinarily convenient for both the cardiologist and the patient. They didn't have to send them off to some hospital and go into the radiology department and get a scan. They had this machine in the back of their clinic, right? And so there's very little negative feedback for getting the test. Right? You want to see that information. The machine's right there. Economically, it's better for the practice if the person has the test, because the CMS, the CMS reimbursement for this test initially was like $1,300. So it was extraordinarily profitable for a private clinic to do these tests. And so everything fed into this growth. In Europe, they don't do this test that much, because actually, between you and me, it's not a great test. But so here's a longer stretch, out into the 2000s. And as this growth continued in usage of this, CMS then started cutting the reimbursement rate right about here. They said, no, we're not going to give you $1,300 for this test. We'll give you $800 or something. And then that had an immediate impact in how the test was, used, in that it was reduced considerably. However, if you look at the rate at which this test is done here, compared to, say, cardiac CT, which is, it's in the noise, it's down here. MR is about here. Stress echocardiography is about here. And so this thing just still completely dominates cardiac imaging. So it's well worth knowing about this technology. So let's look at the physics of how it works. Any questions on that so far? It's a very interesting American healthcare story, right? It's very unique to the United States and sort of fee-for-service, profit-driven medicine. When you go to any country that is not like that, like Canada or anywhere in Europe or something, these numbers are nowhere near like this. They're down here, right? So it was very useful from the patient standpoint, but also very useful from the private practice profitability standpoint. So here's how it works from the physics standpoint. If we have an event in which a photon is emitted, and this is 140 keV photon, and here's our detector. If that photon comes out on this straight yellow line here, and it gets through this thing called the collimator, it will make a flash of light, usually in some kind of detector material, and that light is then detected by something called a photomultiplier tube, and then a signal pulse comes down the wire to your computer. Excuse me. And so that's the basic physics of how it works. And this set of detectors is aligned in this straight line projection such that if I have an event over here and it goes straight towards the detector, I'll detect it at this point on the detector. So you want a projection of the patient onto this angle. And so if I have an event over here, but the photon comes this way, you want to stop that photon, because you don't want to have an excitation occur here. The detector, records an event over here, and it will assume that event came from somewhere along this line in the patient, which is wrong. So that's why this collimator is in place, is to keep the detection limited to those events that occur with a straight line projection down through the patient. This is a really interesting analog device, which changes basically a detection of a gamma ray by a flash in a material like sodium iodide crystal or something like that. So you get a flash of light. What happens here is that light in this material makes an electron eject out of the material, and the electron hits this, it's called a dynode, which is a piece of metal, essentially, that's at a higher voltage than this. That electron hits the piece of metal and causes, say, 2 more electrons or 4 more electrons or whatever to come off of this material. And this dynode is 100 volts higher than this one. So they all fire down towards this dynode. And then each one of those electrons creates a shower itself. And so you get an exponentially growing number of electrons going through each one of these voltage drops. And so by the time you get to the end here, this shower of electrons is considerable, right? So you have a large enough amount of charge to generate a pulse out of this thing. And this is called a photomultiplier tube. And it's been around for a really long time. I used it as an undergraduate physics student to do, laboratories in second year undergraduate physics. And it's still used a lot in nuclear medicine, right? And the basic location of that thing is you have the sodium iodide crystal here, and then this would be the photomultiplier tube, and then a pulse would come out of here when an event occurs, and you have a set of these lined up along here. They're all about 1 inch in diameter, so you can imagine, something that's 50 centimeters around, because we saw, here's the detector here, right? So it's that size, and you have photomultiplier tubes sort of 1 inch in diameter, sort of spread out over this whole thing under here. That's how many you got. And then the part of the system is determining, is the signal that's coming out of that photomultiplier tube, is it from a primary gamma ray that came from the patient? And so if we go back here and we say this primary gamma ray came, made a flash of a certain brightness, and then we get a pulse height, which has the number of electrons here and a charge of a certain amplitude. And so that pulse height we can actually measure on a computer and say, look, if the pulse height is between here and here in terms of that corresponds to energy, essentially, how many photons were created initially in your crystal. So anything in this line we're going to call a true signal, and then that gets changed into a binary or a digital signal and says, yep, I have an event here, and then time goes on, yes, I have an event here. And then these low signals, which we'll see came from scattered radiation or some other source like noise, background noise, those are ignored. Right? So here we have these pulses coming in at a fairly good clip, right? Because the number of photons that are produced per second by the contrast agent you put into the patient can be pretty high. And so a lot of these pulses are coming through. Sorry, the analog to digital converter also knows which detector the signal is from. And so it'll, if the pulse height analyzer says, yep, it's in the right range, it'll put a tick at that box and record it as a signal. And so this is done over and over again, and you just fill up this is just a 1D array, but you can imagine you have a 2D array for this, where you fill up a sort of intensity of detection here. Excuse me. I'm not sure if I'm going to make it the whole way through this, but we'll keep trying. Okay, excuse me, the gamma ray transition for this material. This material is called technetium 99, and there's a number of different nuclear decays that occur in this material, but the primary one produces this 140 keV photo peak that's coming out. You know, a number of photons are coming out of the substance, but most of them are this 140 keV photon. And so this is the peak that we concentrate on and tune the scanner to detect. As you can imagine, we're going to get a set. Let's say we leave this thing here for a minute, right? We'll get a lot of detected signals on this array, and those will represent a projection of the patient along straight lines that are, you know, parallel to these septa that are in the collimator. So we'll leave it here for a minute, get a whole bunch of projections. We build up that sort of signal amplitude projection, and then we'll rotate the entire unit a couple of degrees and get new projections, right? So in this system, we're getting 2 projections at once. You can imagine if it was even more efficient, you could have a detector down here and a detector over there. You would get all of the photons coming out, because they're coming out in all directions, right? So we're doing this, you know, when we have this sepia here, we're wasting a ton of photons, right? Because there's a lot of photons going in every direction, but we're only picking up the ones that are parallel here or parallel here at this time. So here's you know, a sort of cartoon of the organization of the photomultiplier tubes above this crystal that causes the flash of light. And so these sepia, this is you know, these could be made of lead to try and stop photons that are coming in at an angle. And so this collimator is in front of our detector for the gamma rays that causes a flash, and then there's the photomultiplier tube. So you can imagine if you get a flash here, right? This photomultiplier tube and this photomultiplier tube will have some non-zero height of energy, whereas this one over here really won't see that. You'll just get noise out of this one. And so there is the ability to, you know, create a floating point, if you will, or a real number along here where your activity occurs by looking at the relative weights of the photomultiplier tubes. Do we have any questions thus far on that? I don't. I'm not watching for hands to go up. So if you just talk, that would be great. Just interrupt. Thanks. Not going well. So we have these pulses from each photomultiplier tube, and you can imagine there can be many, go through the analog to digital converter. This circuitry, this was all done in a non-digital way for years and years. So, like, nuclear medicine has been around a long time, and so people designed circuits, you know, to do this kind of thing, where you get a weighted average of what's coming in here, and it gives you an X and Y position for where that event occurred. You also look and make sure that all of those things that have that X and Y position sum up to a signal that is an actual event. And so that's like a logic circuit here. It says, yeah, that's an event, so take that X and Y position. And then you basically there's a couple of corrections that you have to do on the signal depending on its energy, right? And to to correct where it is, and then you can make an image. So we got 4 examples here of how these decisions are made and how errors can occur, right? So in the ideal situation, when we have an event or an emission of a photon and it is in the right orientation, i.e. it's relatively parallel to the sepia and the collimator. So we have this go in, it'll get a full energy, it'll pass our energy threshold and go in as an event. This one, because it's coming off at a different angle, will hit the sepia and just the photon will die right there. It just won't go any farther. Now, there is a probability, this is all quantum mechanics, right? There is a probability that that photon is going to get through that sepia. And so if it comes through and it does get through, it can cause a false event. And so what's going to happen, you'll get a spark here or a flash, and the photomultiplier tubes will give you a signal, and then you're going to ascribe that signal. You'll say, it happens somewhere along this line in the patient. And that's just wrong. That's going to be background noise in your final image, right? So the probability with which this occurs depends on a couple of things, but one is sort of the thickness of these sepia, right? So if you make them really thin, then you have high efficiency in collecting photons, but you collect these photons that are not at the correct angle. The other thing that can happen is that the primary photon is emitted from your agent. It travels in the body and then it interacts with, say, an electron in a molecule in this patient, and it scatters off that electron. And so it deposits energy here, like the electron shoots off or something with some energy. And then the new photon from that collision is at the right orientation to get through the sepia and get a detection there. Now, if you're lucky, the amount of energy left in this photon will be low enough that it gets taken out by that energy threshold logic. And then this event isn't recorded because, again, you would record it as having occurred somewhere along this line when that's false, right? It occurred over here. The other thing that can happen is you can get a good signal here. Everything just went right. Here we had a change in energy because we get a scatter of this photon and it comes up here. And so now we have a flash that are coincident. And then the system tries to compute where that flash came from the weighted sum of those signals. And it might pass the energy threshold, right? Because, it has high enough energy, certainly. This is the composition of both these events. And so it would tell you, oh, you had an event somewhere down here, right? And so again, these kind of scatter events cause essentially a cloud of background activity in your image. And so that raises up the background of the image with this fuzzy cloud of scattered events. So if we look at the effect of the collimator, here it's drawn with a different scale. These aren't usually this wide as a fraction of their distance between each other. But for illustrative purposes, they're drawn like this. And the purpose of this figure is to show that depending on your depth inside the patient, right, you will get a different spatial resolution of where that activity occurred. Okay, so here, you see, let me see if I can put a laser. Here we go. So here, we can draw straight lines through the sepia, and we see that we just barely make it through this column and this one, right? Given the geometry of the situation here. When we move to a greater depth inside the patient, away from the detector, then the number of sepia through which this source can get through is wider. And so basically the point spread function, if I have a dot here, this is a tiny little sphere of activity, that I put in the scanner and ask, well, what's the picture of that tiny little sphere? It comes out as a Gaussian blob with a full width at half max. Right here, that is one number that can be indicative of or a report of the spatial resolution. And then this full width at half max is broader, right, at this depth. And so this is important for cardiac because the heart, say the posterior wall of the heart, is a good, 10 centimeters deeper than the anterior wall of the heart. And the anterior wall of the heart is very close to the chest, right? So it can be right up against this thing. But then the posterior wall of the heart is back down here. So if we go back to our example picture of this patient, the distance between the thing we really want to resolve and our detector and our collimator here is somewhere between 10 to 20 centimeters, right? And these graphs show the basically full width at half max of the point spread function of the system. So they can measure this by putting a little tiny sphere in the system and looking at the blurry picture of that little tiny sphere as they move the little tiny sphere away from the detector. Okay, and then so a low number on this graph is good. That means your full width at half max is small, so it's a sharper point, the image, and you can see that depending on the style of anti-scatter grid or collimator, you will get different depth sensitivities. And so this one, obviously, as we go deeper, it gets really blurry, right? By the time I'm down at 20 centimeters, I've got a full width at half max of just under 16 millimeters, right? So it's a pretty blurry thing. But it's also a very efficient one, right? In that it admits, they've used this as the normal one. It's just like, this is 100% detection. Whereas if I use this really narrow collimator, I retain good spatial resolution, but my efficiency is way down here. It's like 25% of this one. So there's a trade-off between letting photons pass through and having high efficiency in detection and the spatial resolution, right? So you have to decide on your system, where you're going to work, and they'll give you different types of collimators you can choose from depending on the application. So here's a slightly different geometry. This one, well, you could probably configure it into the geometry you saw before, but here we've got it so that there's a detector for photons coming this way, and there's a detector for photons coming this way, and they're literally 180 degrees apart. So they're basically getting the same projection for these things. There will be a slight magnification difference, from one side of the body to the other, but you're doubling your efficiency just by putting a detector on the other side of the patient, right? And again, this whole thing, you can rotate it continuously, or you can just stop it and collect and stop it and collect and stop it and collect. We'll look mathematically at how the projection is encoded. And so if we have basically a real number along this line, which is its position along the detector from, say, 0 to 1 or whatever you choose, we create a signal, which is the amount of, the amount of excitation or events that you saw, right, as a function of position along R for this specific theta. And so we're going to click through a set of thetas. We'll take this whole system and click it, say, by 1 degree, theta changes, and then we get a new PR theta function. So mathematically, that's how you want to store your data. This is what it looks like when we look at those two examples I gave you, the pictures of the scanners. So here you have, it's fairly long detector in the Z direction. So this is the patient's head. Well, that's their neck. You can see their neck there, and they have their arms above their head, so they don't get their arms in the way of your imaging. This is the liver here. These look like the kidneys down here. That's a kidney probably. And this is the left ventricle, right? That's the heart. So this, this movie gives you kind of an idea of what your spatial resolution is on that system, right? You can imagine recreating a three-dimensional object from these different projections. Excuse me. The other interesting thing is if you stop this, let me go back to my, how do I just put my pointer on again? I forget, I think maybe hit escape. No. Yeah, it's a pen arrow. There we go. Okay. So you can see the different angular views for each one and look at the heart. If I go this way, it looks like the heart is missing its apex, right? Especially in that something like that view, where go back to here, it looks like it's kind of chopped off. It should sort of stick farther out this way. When we look at it right down the barrel, that this is kind of like a short axis view, but it's obviously dependent on the patient's orientation and their orientation of their heart and their chest. But definitely you can see down the chamber of the left ventricle here. And you can imagine, it looks like this, remember, this is brightness from all of the pieces of tissue that are perpendicular to this plane integrated through the patient. It looks like there's fewer up here than down here, right? So there may be some kind of attenuation up here, but that attenuation, when we look at it and we say it's dark, could be from overlying structures as well, right? So we don't know until we do the three-dimensional reconstruction whether or not that darkness is from the myocardium or from overlying structures. But so that's the raw data at different angular projections. Okay. So what does the projection look like? Here's our gamma camera. This is R along this direction. Here is a cartoon of an object we're going to image. And we have 3 levels of activation in this object. Inside this circle, we have high activation. So there's a lot of photons coming out of this. This is a hole in the object. So there are no photons coming out of this ellipse here. And then there's a background level in the patient. And so you can see when you count up how many events would you see at this point R, right? You do a line integral through the patient here, and a lot of that line includes this high activity. And so the integration of that activity across this line is going to be a high number. When I look at what we call here a projection profile, that P of our theta function, this is for one angle, we get a high value, right? And then when we move across the phantom here, we get sort of a background value. And then when we move our line to go through this void where there's no sample or there's no contrast agent, we get a dip in activity. So this function is our projection that we're going to use to create our image of the object. So remember this thing, a few slides ago, we called this PR theta, this guy here. Those of you who took 280A will recognize this notation as what we used in that course. This, we called it L of L theta, excuse me. But essentially what in CT, when you're doing reconstruction, if you have X-rays entering the body and you have I0 X-rays, like a flux that is so many X-rays per second or whatever, and they're coming into the body here, and you ask, well, how many make it through to this point? It's proportional to how many you put in times an attenuation factor. Right? There's going to be less photons come out here than went in. How much less? Well, we integrate across this line the amount of X-ray attenuation through the body. And that will change as a function of position. So as a function of S, that's the integration variable here. It'll change as a function of position. Also energy, but let's forget about that for the time being. So this number comes out to something less than 1, right? It's like what attenuation occurred to I naught. And that is the fundamental data that we use to reconstruct CT. In nuclear medicine, pretty well the same thing, just in reverse, in the sense that we look at all of the nuclear activity along this line. We detect it on a detector here, and we plot it as an intensity function, right? So we get the same mathematically in terms of the representation of the patient. We get the same type of function, right? It is a projection through the patient. If we look at different examples of that, so here's, say, at 0 degrees, and again, we have an object that looks like this: high activity, no activity, background activity. When we project this way, we see the high activity is in the middle of our detector here. Low activity is off to the edge. When we change theta to 45 degrees and look this way, we now have an overlap of the high activity and the no activity. So we get high activity except a subtraction where we have no activity, right? And then again, just, I don't know, this is about 120 degrees or something. Now the high activity is over on this side of the detector here, and the low activity is here. And so this set of projections is what we're going to use the back projection algorithm to reconstruct the image itself. And that reconstruction is done pretty well exactly the same, using the same principles that computed tomography uses. And if you look at just naive back projection, if I have a dot of activity in my scanner, which on my detector, when I look at along my detector, it maps to some blob, like a Gaussian blob with a full width at half max of my spatial resolution. The dot in my detector, if I take multiple angles of where that dot, shows up on my detector, I can propose an extraordinarily simple way of reconstructing where that dot is. I have 2 angles. I just project the intensity. I just divide the intensity over all of the pixels in the image that are along that angle for that view. And then 90 degrees from there, I can, so this one would be my 0 degrees, and it maps, I'm going to just put an equal value in all of these and 0 everywhere else. And then at the 90 degree one, I'll put 0 everywhere except here where I have my middle one. And then they intersect here, and it gives me a bright signal right there. And so basically, if I have a very small object, I only need 2 views to reconstruct where that object is in the scanner. But this obviously is not an accurate image, right? It has these sort of things off to the side, makes it look like a flag. If I do more angles, right, and project them all in this naive way, then my representation of the object gets much better, i.e. the relative value of this signal versus the background versus these things is better. But I still have a highly artifactual picture. But if I do more and more angles, I will eventually get something that has a relatively smooth background, but a kind of a blurry representation of this object. If we take these things, right, and so these are for different theta values, right? This is still R in this direction, and each one of these is a different theta value. So what I'm going to do is, this is R. So here's my object. And we're going to plot all of these profiles on one function. So R is this way, and theta is this way. And so for each row in this picture, I have a new theta value, and I'll just stack them one on top of the other, right? And that gives me a thing called a sinogram. It's a 2D function of R and theta. And each one of these individual rows is like P R theta, right, for a different theta value. And you can see that, with a very simple object like this, you can see the features in the sinogram that represent these objects, right? As you rotate around and get different angular views of this object, the position of this source, modulates just like a sine wave as we go around, as does the position of this like larger dark source here. And so, here where they're overlapping, right here in this PR theta, if I went through and said, oh, the bright source is right in the middle of the dark source here in this one row, that must be this projection that goes through that puts, excuse me, puts this right on top. I think I'm rapidly coming to the end of how much I can talk, if that's okay. Let's see what we got next. So how do we use this to create this? If we do that naive back projection that we looked at right here, we just take each one of those PR thetas and we just project it back. We get this picture, which is not bad, right? So you look at it, all the basic features are there, but it looks like it's been washed out, right? It has a background that is not zero. There's zero over here. So there's lots of stuff getting washed out into the background, and all the edges and everything are washed out. So it's a very low resolution estimate of the object. And it turns out we need to modify these projections before doing this back projection. We can't just simply back project this thing. We need to modify this projection in order to make this an accurate representation of this. And how we do that modification comes out of what's called the projection slice theorem. And if I have my projection here, sorry that the notation's changed once again, but this is the projection here as a function of position on the detector and my theta. But if this is my object and these are the line integrals through the object like we've collected with our collimated detector, I just take that PR theta, take its Fourier transform, the one-dimensional Fourier transform, and it turns out, and we won't prove it or anything here, that one-dimensional Fourier transform is a sampling of the full two-dimensional Fourier transform of your object. And it's a sampling through that two-dimensional Fourier transform at this angle theta. And once that is understood, it becomes clear how we should do the projection reconstruction. We just can't project these back. We need to modify them. And I won't go into it, but it turns out that when you look at what does it mean mathematically to take these samples that are these radial samples in Fourier space of your image. And so if I have my image is here, and this is my Fourier transform of the image. If I want to do an inverse Fourier transform of this to get my image back, because I have these radial samples, I need to do it in polar coordinates. And I need to use the Jacobian for polar coordinates, which includes this, which is a weighting of the data such that it is zero at the origin and it gets linearly larger as we move out to these higher frequencies out here. So this is the accurate formula to create our picture using the inverse Fourier transform of the data we have sampled. And so that means this thing it's become known as the Ramlock filter, and it essentially is an inverted, it's a triangle that looks like this that you apply to the data in order to get the reconstruction correct. And if you look at what happens when you apply this Ramlock filter, in the Fourier domain before you do this back projection, if you apply it to all of your data and do the back projection, you get a very high resolution representation of the object. However, the problem is that if you have random noise out here at high spatial frequencies, it amplifies that noise extraordinarily because of this the nature of this filtration. And so what's normally done is in the Fourier domain or in the spatial domain, if you do convolution, you roll off these high frequencies so that you get a picture that looks more like this. Right? Sorry, this is a brain, but same thing done in the heart. This is just a good example of high frequency noise, what it looks like when you just do a reconstruction without any roll off of the ramp filter. And so normally what you do is you pick one of these filters and you get a sort of a rationally smoother picture. Then it will do one more thing, and then I'm going to have to sign off, I'm afraid. The other artifact that shows up in nuclear medicine is the fact that all of the voxels in your patient that are deep inside the patient, in order for the photons to be detected from here, they must pass through a lot of patient, right? Compared to the photons that are generated out here at the edge of the patient. These photons can just emanate from the patient, at least in these directions, without a high probability of being reabsorbed by the patient. And so what this does is when you have an object that has uniform activity and you do a naive reconstruction without doing a correction on the data that is weighted by depth, that tells you, you've got to take into account that the probability of attenuation from here is much higher than it is from here. You'll get a function that looks like this, right? So really high activity on the edges, lower activity in the middle. This you can determine if you have a picture of the patient, say from CT, from computed tomography. You can create a correction algorithm that just looks at a point and says, what is the relative probability of attenuation in this direction through the patient? And you just correct for that at that pixel. And then what that does is it creates a new image that basically has that correction factor in it and gives you a uniform activity if it is truly a uniform object. And this is really important for cardiac. And I want to show you a couple of examples. I think I had one here. Do I have one? Yeah, so here's, this is a short axis view of the left ventricle, right? Where we have activity as a function of position. This is the chamber of the heart. This is the myocardium. And this is the rest scan. This is the stress scan. And these two scans are what you get if you don't correct for the probability of attenuation. Remember, this is deeper inside the patient because this is the bottom of the heart, right? This is their posterior wall of the heart. This wall is close to the chest. It's up here. If you don't do that attenuation correction, then you get these pictures. When you perform accurate attenuation correction, those pictures look like this. And you can see that is fundamentally different, right? Because this one, you would say, it looks like there's low flow in the posterior wall of this patient's heart. This one looks absolutely normal, as does this one, right? So even it's normal at rest, normal at stress. And so it is very important that this attenuation correction is done well. And it's often done with a CT scan. These are other examples. Let me see if I have, well, I don't have one there. These are other examples of when you've done the attenuation correction using the CT and when not. And you can see there's considerable difference in the two maps, right? And this one, remember, this is that bullseye map. You can see there's a fairly large area in the posterior wall. It's often in the posterior wall because it's deeper, that actually is normal, right?